So in this week of lectures, we have been discussing about direct products, which is part of application of group theory into quantum mechanics, right? So let us discuss little bit more about direct product, which we have not covered. Some results from direct product applications, not applications, but direct product results on to group theory. So let's start with tutorial 7, and we will say more about direct products. So by now we all know what are direct products in case of matrices or in case of traces of matrices. How do we obtain the direct product? So let us directly go and discuss the results of these. So when we are discussing these results, let us take an example of let's say C4V point group. So it has all sorts of 1D and 2D IR representation. So let's take an example of C4V point group. So let me write down the character table of this, which is E, 2C4 and C2, 2 sigma V and 2 sigma D. And this side we have A1, A2, B1, B2 and A. And we have 1. This is called as totally symmetric representation, so all ones. Then we have A2. So A2 will have sigma V's as negative. Then B1 we have -1, 1, 1, -1. For B2 again you have -1, 1, -1, 1. And this is a degenerate representation, so this will be two-dimensional, 0, 0. Okay, so let us see the first result of direct product. So it says, I'll first write down the statement and then we will discuss using C4V example. So it says, if all the combined irreducible representations are non-degenerate, then the product will be a non-degenerate representation too. So of course, if it is a non-degenerate, it will be an IR representation, that is irreducible representation. So what does it mean? So it's saying that if all the combined means for which we are calculating the direct product. So if we are calculating the direct product of irreducible representations which are non-degenerate. So what is non-degenerate? So non-degenerate means one-dimensional IR representations, right? So then the product will be non-degenerate representation too. So let us see an example. So let's say if we are making a direct product, or if we are combining A2 with B1 with B2. Okay, so what do we have here? So let's try to combine this A2, B1, B2. So you have 1 into 1 into 1, so that is 1. Then you have 1 into -1 into -1, so that is 1 again. 1, 1, 1, so 1 again. -1, 1, -1, so you have 1 again. -1, -1, 1. So you have 1 again, right? So this gives rise to 1D representation. So all of these are non-degenerate representations. So any combination of non-degenerate or one-dimensional irreducible representation will give you a non-degenerate representation. Okay, so this gives me A1 directly, right? All of these are. So let us do one more calculation. So let's say This time we are combining only B1 and B2. What do we get? So you have 1, 1, 1, minus 1, minus 1. What are we getting here? 1, 1, 1, minus 1. So this gives you A2. Right? So again, it's a one-dimensional representation. So you can take any combination. Let's say if you are doing A2 into B2. So again, we are combining two one-dimensional representations. So now this is 1 into 1, 1 into minus 1, so minus 1, 1 into 1, minus 1 into minus 1, so that is 1, and minus 1. So this is second and fifth place as minus 1, so you have B1, right? So if you keep on combining different one-dimensional representations, you will always be getting one-dimensional representations back, which is obvious because your matrix size is not increasing. If you are combining one-dimensional matrix, multiplying one-dimensional matrix with one-dimensional matrix, the product will be one-dimensional matrix. So it will have to be a one-dimensional or non-degenerate irreducible representation. So that is first rule. Okay, first result of direct product. All right. So then second is, again, let me first write down the statement and then we will explain. The product of a non-degenerate and a degenerate representation is a degenerate representation. So now we are combining a one-dimensional representation, non-degenerate, and more than one-dimensional, a degenerate representation. So if you combine one-dimensional and, let's say in this case it's two-dimensional, but you can also call it as 3D. So this is 1D. This can be 2D, 3D, 4D, anything. Okay. So if I'm doing this, then the result is corresponding 2D, 3D, or 4D. Now again, let's take an example and see. So let's say if we do B2 into E. B2 into E. So what do we have? So 1 into 2, we have 2. Minus 1 into 0, so you have 0. 1 into minus 2, so you have minus 2. And then 0, 0. So because C4V point group has only one degenerate representation and you are bound to get a degenerate representation, so you will, no matter what one-dimensional representation you choose here, you will always get E, right? So let's take another example here. Let us say if we have A2 direct product with E. So A2 is 1 into 2. So you have 2. Again 1 into 0. 1 into minus 2. Minus 2. And minus 1 into 0. Minus 1 into 0. So again you are getting E. So irrespective of what you have at this position, because there is only one degenerate representation, you are going to get E degenerate representation back, because the product of a non-degenerate and degenerate is supposed to give you a degenerate representation only. Of course, if you have multiple degenerate representation, then you can get any other. Let's say if you have in some point group, if you have E1 and E2. So if you now combine something with E1, you might end up getting E1 or E2, because now there are two options, right? So depending on what is the result, what is the product, you can either get one of the two degenerate representations. I hope this is clear. So you can keep on taking any example and see if all the rules are verified. So third is the direct product . of any representation with the totally symmetric representation is the representation itself. That means if you now combine any of this representation, let's say A2, B1, B2, E, with totally symmetric representation. There is only one totally symmetric representation in each point group, and there is always one totally symmetric representation in every point group, right? So if you combine any, or if you take a direct product of any irreducible representation, it can be degenerate or non-degenerate. If you take direct product of any representation with totally symmetric representation, you will get that representation back, right? That is very simple to see, because let's say if you are multiplying A2 into A1, so all the characters are multiplied by 1, so that is not going to change anything. So A2 into 1 will give you A2, B1 into A1 will give you B1, B2 into A1 will give you B2, E into A1 will give you E, and so on and so forth, right? So that is very, very easy to see. So let me just write down this. So A1 into any representation is equal to same representation. So this is also very simple to see. Okay. Now let's say the fourth one. The direct product of degenerate representations is a reducible representation. So far our direct products were not giving any reducible representation. They were giving either 1D representation or degenerate representation, but from the character table itself, right? We don't have to reduce that. But if you take a direct product of any two degenerate representations, then this will give rise to a reducible representation. So that means in this particular case, we have only one degenerate representation. So if we combine E into E, if we take direct product of E and E, then whatever result you will get will be definitely it has to be a reducible representation. That means now you can reduce that representation into component irreducible representations using reduction formula. So this means if I take E cross E, then I will get 4, 0, 4, 0, 0. Now this is a reducible representation. So using reduction formula, you can now get A times A1 plus B times A2 plus C times B1, D times B2 plus E times E, right? So of course you have to calculate these coefficients A, B, C, D, E. Some of them will be 0, some of them will be some other numbers, integral numbers, but it will give rise to a combination of A1, A2, B1, B2 and D. So that can be easily done. That we have seen in last tutorial also how to do that, and we have learned in lectures. Okay. So that is fourth. And fifth one is the direct product of an irreducible representation. This rule we have already seen, but I am just listing it out for completeness. Will not explain it with itself. Is or contains the totally symmetric representation. So if you're taking direct product of an irreducible representation with itself, it might result into a totally symmetric representation, or it will contain, when I say contain means, if you end up getting a reducible representation, it must contain A1 if and only if the direct product is of two irreducible representations which are same. That means direct product of a reducible representation with itself will contain totally symmetric representation, right? This case we have already discussed in last lectures. We have also derived an expression for this. So let's not go into those details, but just for completeness, I will write that if you take A2 into A2, you can just close your eyes and write it down as A1, okay, without calculating. B1 into B1 will be A1. See, why am I saying that? Because B1 into B1 both are two one-dimensional representation. It is bound to give you a one-dimensional representation, and the rules also says that if I'm combining two same irreducible representation, it is also bound to give me a totally symmetric representation. So no matter what you do, you will always get A1 if you combine two same IRs, right? So similarly, now if I do E1, E into E, my coefficient A here will definitely be non-zero. Okay, so that means A plus B A2 plus C B1 plus D B2 plus E times E. So in this case, I can say that A will definitely be non-zero, because it must always contain A1, because you're combining two irreducible representations which are same, that we have seen earlier. And the last one also is a corollary of this fifth one only. Only the direct product of a representation with itself is or contains the totally symmetric representation. Okay, so what do I mean here? So that means if I'm taking a representation which is not the same, so for example, I can say that A2 into B1 will never be equal to A1, right? Similarly, B1 into B2 will never be equal to A1. So totally symmetric representation will only come as a result if the direct product is of a representation with itself. Otherwise, it will never come. So basically, it's opposite of this. Fifth and sixth are the same things input in different words, right? So that makes the calculation of direct products little easier. So I hope these results will be clear, and I leave it to you as a home exercise. Pick up a character table, let's say OH, so that it's a big one and you have almost everything in there. So pick up a character table OH and show that above 6 properties of direct product holds true. Okay, so that can be easily done. So just go find a character table. If you don't have any book, you can just Google character table octahedral point group, and you will see that Google will spit out the character table, and just use that character table to see if all the above 6 properties are verified using any of these character table. Okay, so that is your home exercise. In next week's lectures, we'll be looking at direct product applications. So before that, please do practice these properties so the application part will become very easy. All right, that is all for today. Thank you very much.